Hello everyone, I am Dr. A.K. Srivastava, physicist in the Department of Radiology, University College of Medical Sciences, on basic concepts of magnetic resonance imaging. MRI plays a very vital role in the patient care. Some of the biggest advantage of MRI is it provides excellent soft tissue pathology. It doesn't need any ionizing radiation, and direct imaging in any plane is possible on the basic principle of MRI. MRI is based on nuclear magnetic resonance. This is the interactions of hydrogen nuclei in our body that provides the images based on G-man level of nuclear spin. Objective of this module is, after completing this chapter, reader should be able to understand the position of nuclei in high magnetic field, trace the steps involved in production of magnetic resonance signals, solve the Larmor equation to find a resonance frequency, and define T1 and T2 relaxation times. The first is that how the interaction of nuclei with a strong static magnetic field takes place. The nuclei of atom with an odd number of protons or neutrons exhibit an intrinsic property called spin angular momentum, which causes nuclei to spin about its axis. For a non-zero spin quantum number, the nucleus is associated with a magnetic moment and thus poses a magnetic dipole moment, like Earth has a spin angular momentum which causes Earth to spin about its axis and causes day and night rotation, and also have magnetic dipole moment. In a simplified way, we may say that nuclei with an odd number of protons or neutrons behave like tiny magnets. However, in a sample, these nuclei are randomly oriented in absence of magnetic fields, hence there is no net magnetization present in the sample. In MRI, it is assumed that the patient is placed along a z-axis and extended magnetic field is applied along the patient. Hydrogen nuclei are randomly oriented in the patient body in absence of any magnetic fields, hence there is no magnetization present in the sample, and therefore net magnetization is zero. In this figure, you can see the hydrogen nuclei are randomly oriented, and therefore net magnetization present in the sample is zero, which we can say that tissue does not have net magnetization, or tissues are not magnetized in absence of any magnetic field. According to law of quantum mechanics, when hydrogen nuclei placed in a strong magnetic field, we call it as V0, the magnetic moment of hydrogen nuclei aligned with this magnetic field parallel or anti-parallel. You can see in this figure some nuclei along the direction of main magnetic field, some of them aligned anti-parallel to the main magnetic field. Those which aligned parallel to the main magnetic field are said to be in the lower energy state. On the other hand, those nuclei which aligned anti-parallel to the main magnetic field, they are said to be in the high energy state. For the nuclei to have, some of the nuclei have little more nuclei aligned parallel to the main magnetic field. You can see in this figure more nuclei aligned parallel to the main magnetic field than anti-parallel to the main magnetic field. The alignment of magnetic moment is measured as the total of the magnetic moment and is expressed as a vector sum. This is very small population difference which gives rise to net magnetization in the direction of main magnetic field, and therefore the component of all the proton cancelled out and longitudinal magnetization vectors add up, and excess of hydrogen nuclei which were along the direction of main magnetic field line up parallel to B0 and create net magnetization vector of the patient. You can see in this figure some more nuclei aligned along the direction of main magnetic field than anti-parallel to the main magnetic field. Since proton behave like tiny magnets, the exact alignment in external magnetic field of the tiny magnetic moment causes these magnets to precess about the magnetic field. You can see in this figure, this precessional magnetic field is very interesting. Its precision requires spin angular momentum and the torque perpendicular to angular momentum. Angular momentum of the nucleus is determined by the spin of unpaired protons and neutrons, and by the orbital angular momentum of neutron and proton. What is precession? The precession is when protons rotate around themselves and also their axis of rotation moves such that it forms a cone-like shape. This movement of axis of rotation of proton is called precession. As you can see here in this figure, this precessional motion is the third motion, which is the spin angular momentum is spinning about its axis. Then there is a dipole moment and magnetic dipole moment, and then you have the precessional motion. The frequency of this precessional motion is equal to the gamma is equal to the gamma into B0. This is what is called Larmor frequency. The number of protons of the position of proton per second is called precessional frequency, and this is expressed in terms of hertz. The gyromagnetic value is a unique value for each type of nucleus. For example, at 1 Tesla magnetic field, the frequency is 42.57 megahertz. At 1.5 Tesla, it is 64 megahertz. At 3 Tesla, it is somewhere around 127.7 megahertz. So this is the frequency which is unique for hydrogen nuclei. Other nuclei which are also present in our body, but their Larmor frequency is different. So hydrogen is unique in this way that it has a high abundance, and therefore you can see the frequency of precession is very high, and therefore the hydrogen nuclei is chosen to produce MR signal in MRI. This is very important for us, and therefore we can say that the hydrogen nuclei in our body behave like a magnet, and there is a more nuclei aligned along the direction of main magnetic field, and therefore there is a net magnetization, and these net magnetization is small nuclei which are precessing. They are precessing, but with a frequency 42.58 megahertz with 1 Tesla, and these nuclei, but they are not precessing in phase. So what happens is, the next point is interaction of nuclei with a strong static magnetic field, which is called resonance and excitation. What is resonance? This resonance is a very important part of MRI. This tells you about the exchange of energy between two systems at a specific frequency called resonance. It is a phenomena that occurs when an object is exposed to an oscillating perturbation that has a frequency close to its own natural frequency of oscillation, and in this net magnetization vector is flipped to get information by applying radio frequency pulse perpendicular to the external magnetic field. This RF pulse makes the individual nuclei to precess in phase, and there is a RF coil to generate the RF pulse, that is second magnetic field, which must be matched with the Larmor frequency of nuclei, that is 63.86 megahertz per 1.5 Tesla. If RF pulse having frequency equal to Larmor frequency of nuclei is applied perpendicular to the external magnetic field, it is absorbed by hydrogen protons and therefore resonance occur. Now at this point, this we can call it as the excitation. The nuclei are excited. Due to resonance excess, nuclei excited from lower energy state to high energy state causes excess nuclei aligned towards XY plane that get formed transverse magnetization perpendicular to the magnetic field. The rotating angle, also known as a flip angle, depends upon the RF pulse, strength of RF pulse, and the orientation and the duration for which the RF frequency is applied. Now you can see a net magnetization is established. This net magnetization is excited, is flipped by applying very high RF pulse, and the frequency of RF pulse is matching with the Larmor frequency, and therefore the net magnetization will be flipped towards transverse plane, which is called transverse magnetization. So it is absorbed by the hydrogen proton and resonance occur. Now excitation. Due to resonance, excess nuclei excited from lower energy state to high energy state causes excess alignment towards XY plane. You can see in the figure the net magnetization is flipping up towards the XY plane. That gets from transverse magnetization perpendicular to magnetic field. The rotation angle, also known as flip angle, depends upon the RF pulse strength and its orientation. You can see the hydrogen nuclei are flipped to XY plane, and this causing transverse magnetization applying the RF pulse. Now this is the flipping of net magnetization towards transverse direction, known as transverse magnetization vector, and in this figure I have applied 90 degree RF pulse. That means the nuclei are flipped by an angle of 90 degree. It can be less than 90 degree or it can be 180 degree depending upon the pulse sequences we choose. For example, in spin echo, this angle is 90 degree. For inversion recovery pulse sequences, this angle maybe is 180 degree, and in gradient recall echo pulse sequences, this angle is less than 90 degree. So this flip angle is very important, and this flip angle, this flipping is done by applying radio frequency, which is perfectly matching with the Larmor frequency of hydrogen nuclei. Now at this point of time, radio frequency pulse is switched off. When the radio frequency pulse is switched off, this process called relaxation. It is the process that occur after terminating the RF pulse, in which physical changes that were caused by the RF pulse return to the state from where they were disturbed, and that means the relaxation means and recovery of proton back towards the equilibrium position after being disturbed by RF excitation. And when the RF pulse is switched off, transverse magnetization is reduced, which is called transverse relaxation, decay of transverse magnetization, where longitudinal magnetization increases, which is called longitudinal relaxation. So you have two processes that are occurring together almost simultaneously, but it is a different process. In one process you have the decay of transverse magnetization. This decay of transverse magnetization is due to loss of phase coherence of hydrogen nuclei, which were made to process in phase after application of radio frequency pulse. Now they are going out of phase, causing transverse magnetization to decay. Another process almost simultaneous but different is the return of hydrogen nuclei from excited state, which were you can see in the earlier I have mentioned that the RF pulse made them to flip from lower energy state to high energy state. So relaxation takes place, as I explained, takes place by two processes almost simultaneous. One is called spin lattice relaxation time, which is called T1. When RF pulse is switched off, proton losing their energy, and this energy is given to the surrounding lattice. This is why it is called spin lattice relaxation. As proton lose their energy, the longitudinal magnetization increases, hence it is called longitudinal growth of longitudinal relaxation. It is the time for 63% of nuclei to return to the lower energy state is called T1. It depends on tissue composition, structure and surrounding lattice. If the lattice has magnetic field which fluctuate at larger frequency, then transfer of thermal energy from proton to the lattice is very easy and therefore is fast, and therefore longitudinal magnetization is shorter. Another type of relaxation is called spin relaxation, called T2. The nuclei which were processing in phase because of RF pulse starts losing their phase coherence after the RF pulse is switched off. Loss of phase coherence by the nuclei cause decay of transverse magnetization. It is called decay of transverse relaxation. It is the time in which transverse magnetization decays to 37% of its original is called 1T1. This 1T2, it depends on the magnitude of external magnetic field and inhomogenities of total magnetization which within the tissues. You can see the T1 relaxation time in which there is a growth of longitudinal magnetization, and which is of course called T1. So different tissues have different T1 and depending upon the difference of T1 we get the contrast on MRI. Then another figure tells you about the decay of transverse magnetization. So you can see here the transverse magnetization from the time in which it decays to 37% is called transverse magnetization. In case of longitudinal magnetization, this is the time longitudinal magnetization recovers 60% of its original value. And you can see now after T1 and T2, we can see what is free induction decay, FID. The primary MR signal is called free induction decay. Very fast, cannot be measured. The signal is set at maximum strength immediately following excitation and decays to zero relaxation process. The decay of FID is due to loss of phase coherence of individual spin over time. But here it is not only decays due to transverse magnetization or loss of phase coherence of hydrogen nuclei, but it is because of the combined effect of intrinsic magnetic field inhomogeneity and extrinsic magnetic field inhomogeneity, and both these factors combined and led to decay of MR signal very fast, which is called free induction decay. Now next part is the image reconstruction. How do we reconstruct the image in MRI? We call this happens in the steps. One is the encoding steps. The first is the slice encoding step. In this way, single slice is excited. You can see in this figure, this gradient has gradually increasing magnetic field strength from one end to another end. It determines the slice position. Slice thickness is determined by two parameters. One is the bandwidth of RF pulse and second is the gradient strength along field of view. So this gradient magnetic field, if it is applied along z-axis, one can select the slice along z-axis, or we can say transverse axial images. So in transverse axial image is selects the slice in the, you can see in this figure the gradient magnetic field has been applied along z-axis to cause the FOB is to divide in the slices. So this is how we can select the slice by applying the gradient magnetic field along z-axis. This slice select gradient is on at the time of sending the RF pulse, slightly before the application of RF pulse. So we can select the slice. So the next is to slice the cut, cut the slices into columns. So first is the phase encoding gradient, second is the phase encoding gradient. This gradient is turned on for a shorter period of time after slice select gradient is on. Slice select gradient cuts the slices into phase encoding gradient cuts the slices into rows, and then this phase encoding gradient exactly is applying along perpendicular to the z-axis, and this 90-degree RF pulse then switched on, gradient turned on, and this is applied for a very short period of time. At the time then next gradient is on. So before the next gradient is on, this slice is cut into rows. Now third step is frequency encoding gradient. This is the slices into columns. This gradient will cause proton in a different vertical columns. So now we have cut the slices first into the FOB is cut into z-axis along the cut into slices, then slice is cut into rows by applying phase encoding gradient, and then the slices are cut further cut into columns by applying frequency encoding gradient. So all these three gradients are applied to select the slice, to address the MR signal to a particular slice. I mean, how does the MR signal know where from this signal is coming from? So this is done by applying the gradient pulses along the different directions to select the slices into different directions. Like in case of transverse axial slice, the gradient is applied along z-axis to select the slice along transverse axial plane by applying the gradient along z-axis, and then this slice is cut into rows by applying phase encoding gradient, and then the slice is cut into columns by applying frequency encoding gradient. Now you can see the information of each phase and frequency is encoded into the signal. For acquiring a matrix of data element, it is thus finally required to collect a series of points in the presence of readout gradient, which is called a frequency encoding gradient, that encodes the frequency of signal and produces a series of spatially encoded data points following Fourier transformation. This Fourier transformation is an image processing tool which is used to in terms of sine and cosine functions. Each data point contains phase and frequency information from whole slice at a particular time, during which readout frequency amplitudes are represented in time domain. The fast Fourier transformation mathematically converts the frequency amplitude into frequency domain. This is necessary because gradient spatially locate signal according to their frequency and not according to their time. The Fourier transform plane of the acquired signal intensity pattern each at different spatial frequency, which is inverse of Fourier transformation. Thus, Fourier transform to yield the image. In the MR image formation, there is a temporary image space called K space, usually a matrix in which data or in the form of digital MR signal is temporally stored. When K space is full at the end of the scan, the data sets are mathematically processed to produce a final image. Signal corresponding to low spatial frequencies are concentrated near the origin of K space. Information about the high spatial frequencies is spread further away from the origin. The manner in which data at every point in the K space contributes to the image depends upon its location. Fourier transform plane or K space point at the edge of the Fourier space determine image resolution, while those towards the center contributes to image contrast. We can see here the Fourier transformation images. You can see how the frequency is encoded on frequency domain, and the frequencies, these information are stored in the K space, and these information are utilized to reconstruct the image. You can see here in this the patient, the image of the head scan is reconstructed from K space to data space, and then this data space is converted back into the analog signal, and which is represented in the grayscale images. So this is how we can see here this. First of all, I told you that the MR signal is generated by hydrogen nuclei, and these hydrogen nuclei are excited by the RF pulse, and that is what is called the resonance. At the resonance, the nuclei are excited, and then when relaxation occurs, the hydrogen nuclei are losing their phase coherence, and therefore that is what is called T2 relaxation time. And when the nuclei which were excited from low energy state to high energy state coming back to their original state, and this is called the T1 relaxation time. Now coming to the basic pulse sequence. Basic pulse sequence means it is the spin echo pulse sequence. In a spin echo pulse sequence, as you can see in this figure, first of all the 90 degree RF pulse is used. What does this 90 degree RF pulse do is that this 90 degree RF pulse completely brings the longitudinal magnetization towards the transverse plane, and then subsequently 180 degree RF pulse are used. So there are two factors. One is the TR, time between two successive 90 degree RF pulse determines how much longitudinal relaxation time will occur before constructing the next rows of image. TE is the time between the peak of 90 degree RF pulse and peak of echo that is formed. The spin echo, as I told you, a 90 degree RF pulse that were in phase begins to dephase in the transverse plane. After a certain amount of time, if a 180 degree RF pulse is applied, the spin will rotate over to the opposite axis. Now, rather than the spin contributing to dephase, the spins will begin to rephase, and the spins which come back together after some time, and this is the signal is measured at this point of time with the receiver coil, will increase from a maximum signal and then decrease as the spin once again dephase. At this time, 180 degree RF pulse could be applied to rephase the spins again. So rephasing of spin turns forms an echo called the entire sequence called a spin echo pulse sequence. You can see the pulse sequence. 90 degree RF pulse is first applied, then 180 degree RF pulse is applied. Now another sequence is called inversion recovery pulse sequence. In inversion recovery pulse sequence, as you can see, the name itself implies we have two type of inversion recovery pulse sequence. One is called STIR, short tau inversion recovery pulse sequence, and FLARE, fluid attenuated recovery pulse sequence. Herein 180 degree RF pulse causes an initial inversion of longitudinal magnetization. the magnetization then begins to grow back in the direction of main magnetic field, and by applying 180 RF pulse. The magnetization of different tissues will grow back at different rates. When signal from the tissues to be suppressed crosses the 0 axis, then applying 90 RF pulse will rotate all the signal into the transverse plane. Since the signal from tissue at 0 point is 0, and therefore there is nothing to rotate into the transverse plane, this way the tissue will be specifically suppressed from the image. This will not contribute to any signal brightness on the signal. The acquisition parameter in this case is the time between application of 180 RF pulse and 90 RF pulse is known as time of inversion. And after 90 RF pulse, you can see it is a spin echo pulse sequence, and again the signal is dephasing and then rephasing, and this rephasing at that point of time echo is generated, MR signal are detected. So this detection of MR signal is utilized to generate the image in a different tissue parameter. We call it as STIR. STIR is the short time of inversion recovery pulse sequence. Here what STIR means, it is the time of inversion is very short. For example, let's see the STIR. If I want to suppress the fat from the image, I'll use STIR pulse sequence. What happens is that the STIR, the time of inversion is usually 0.693 of T1. For example, in case of fat, this time is roughly about 250 into 0.69, something about 180 millisecond. For CSF, this T1 is very long, it is about 2000 millisecond or more, and in that case the when tau inversion recovery pulse sequence is used, that means the time of inversion is 180 degree millisecond, and in that case at that particular point of time the fat is passing through 0 signal from minus 180 degree to plus 180 degree to 0 degree. So this is what is called the return of longitudinal magnetization. Longitudinal magnetization is returning from minus mx minus mz to plus mz through 0. So when for fat, for instance, if 180 degree or pulse 180 millisecond time of inversion is utilized, in that case the fat is passing through 0 signal, and at this point of time the 90 degree RF pulse is applied. On the other hand, the CSF, which has a significant signal but along the minus longitudinal direction, and therefore CSF would be brighter on the image, the fat is darker on the image. You can see fat is normally suppressed from the image. So this is used for fat suppression technique. On the other hand, if I want to suppress the fat, I'll use FLAIR, fluid attenuated inversion recovery pulse sequence. In fluid attenuated inversion recovery pulse sequence, here the time of inversion is longer, much longer. For example, for CSF this time is about 1500 millisecond. So in that case the CSF is passing through 0 from minus mz to plus mz, whereas the fat has already achieved most of its longitudinal magnetization, whereas the CSF is passing through 0, and at this point of time 90 degree RF pulse is applied. So what happens is the signal from fat is very high, however signal from because the longitudinal magnetization for CSF is 0, and when 90 degree RF pulse is used, it doesn't excite anything, and therefore the signal from fat is 0, because when you excite again there is no meaning in excitation, and therefore the signal from CSF would be 0. Now third is the gradient recall pulse sequence. In GRE pulse sequence, it includes an initial RF pulse which flips the angle of something like less than 90 degree RF pulse and the lack of 180 degree RF pulse. This is very interesting, that there is no 180 degree RF pulse. Instead, the smaller flip angle and lack of 180 degree RF pulse allows the TR to be much shorter, resulting in a very fast imaging time, even though there is no 180 degree RF pulse is used to produce a spin echo. Gradient pulse used to dephase and rephase the signal in the transverse plane to form the gradient echo. In this figure you can see less than first of all less than 90 degree RF pulse is used, which is to slightly flip, less than maybe 60 degree is flipped. So in this case both transverse and longitudinal magnetization are present at a time, and then magnetic fields are used in one direction. So nuclei which were precessing in phase, they start dephasing, and when this magnetic field is reversed, the reversing of magnetic field causes these nuclei to rephase. So this rephasing or dephasing causes the gradient echo pulse sequence. Now next is the T1 weighted image. How do we get the T1 weighted image? This image is having T1 weighted image. Here you can see here, this is the T1 weighted image. This is achieved by using short TR and short TE. Short is 10 to power minus 10 to 30 millisecond, and long T1 you can see in this one the longitudinal T1 weighted image. This is achieved by using short TR and short T. On the other hand, T2 weighted image, you can see in this figure, this has been used by using long TR and long TE. So the tissue having long T2 will produce more signal as compared to the tissue having short T2. On the other hand, on T1 weighted image, the tissues having short T1 will be more brighter than the tissues having long T1. For example, fat would be brighter on T1 weighted image. On the other hand, fat would be darker on T2 weighted image. On the other hand, CSF would be darker on T1 weighted image and will be brighter on T2 weighted image. So in this case, this is how we get the T1 weighted image, T2 weighted image. Now coming to the last section is the system hardware. The main requirement of an MRI system as shown in this figure is that main magnets, which are very high magnetic field, zinc coils, and you have the gradient coil, RF coils. So we have the three main magnetic field. One is the main magnetic field, which is in the order of 1 Tesla to 3 Tesla or more than 3 Tesla. Then second is the shim coils that are actually used with the main magnetic field to make it more homogeneous. Second is the RF coils. The RF coils are utilized to produce to excite the MR signal, and then you have the gradient coil that selects the slice, and then slice is cut into the rows, and then the rows are cut into columns. So first of all is the magnet. It is the heart of the MR system. For any particular magnetic type, performance criteria includes that signal, temporal stability, and field homogeneity. Magnets may be permanent, resistive coil magnets, superconductive coil. Mostly the superconductive coil are used. Superconductivity is a characteristic of certain materials like niobium titanium alloy that when maintained at extremely low temperature exhibit no resistance to electric current. Superconducting temperature is 4 Kelvin, that is -269 degrees Celsius. To maintain superconductivity, cryogens are used. Liquid helium and liquid nitrogens are used as a cryogen. Sim coils. Sim coils interacts with the main magnetic field to improve the magnetic field homogeneity over the volume of interest. used for the patient imaging. The process of making magnetic field homogeneous is known as shimming. It can be achieved by metal disc or plates. We call it as passive shimming, and solenoid called active shimming, to make the main magnetic field more homogeneous. Then we have the gradient coils. These are contained within the main bore magnets to produce linear variation of magnetic field strength across the useful magnetic volume, and magnetic field gradient is obtained by superimposing the magnetic field of two or more coils carrying a direct current of a specific amplitude and direction. The gradient strength is determined by peak amplitude, and the slope of typically ranges from 1 to 50 millitesla per meter. Third is the RF coils. These RF coils are used to transmit RF pulse as well as to receive the returning signals. Two types of RF pulse are used. One is the RF transmit coil only. In these cases, the RF coils are transmitted. These creates an oscillating secondary magnetic field by passing an alternating current through a loop of wire. For excitation and resonance, created secondary magnetic field, it must be arranged in such a way that it is at right angle to the main magnetic field. Then RF receiver coil. If a loop of wire is exposed to an oscillating magnetic field, a current is induced in the loop. This receiver coil in this way is used to detect MR signal. Fourth is the patient table. All the systems are uses hydraulically or mechanically driven couch to lift patient to the level of bore of imaging system. The tables are comfortable for the patient and allow for the attachment of coils and immobilizing devices. Other components in MR system are computer system, pulse control system, and error processor, and image processor, hard disk drives for storage of raw data, operator control for user interface. Now summary. To summarize this lecture, first of all, I told you that nuclei have intrinsic spin angular momentum. Nuclei with magnetic moment turn will precess when placed in a strong magnetic field, and this precision may be detected by when it is induced by an electric signal in the form of MR signal, which is an oscillating magnetic field. Then Larmor frequency is product of gyromagnetic ratio and B0, which is the main magnetic field. Patient is placed in a strong magnetic field. Nuclei establishes a net magnetization along the direction of main magnetic field, which is called longitudinal magnetization. This longitudinal magnetization is flipped by using radio frequency pulse to generate the transverse magnetization, and then after switching off this one, relaxation occurs. Here due to loss of phase coherence, we get T1 relaxation time and T2 relaxation time